Welcome to my video course on mastering ERTMS/ETCS signaling systems. I'm absolutely thrilled to have you here for this explainer. Today, we're diving deep into the ground-based infrastructure, specifically the trackside architecture of the ETCS command, control, and signaling system. If you really want to understand how high-speed trains safely navigate incredibly complex networks, well, this is exactly where it all begins.
Here's our agenda for today's session. 1. An overview. 2. The ETCS subsystem. 3. Interlocking. 4. Traffic management. And 5. Subsystems synchronization.
Let's jump into Section 1, Overview, the big picture.
Notice how clearly we can separate the two main halves of the high-speed railway transport system here. Over on the right, you've got the train-borne subsystem, the computers and sensors physically riding along on the train. But we're focusing our attention entirely on the left side today, the trackside subsystem. We have three completely distinct functional blocks. There's the green ETCS and IXL blocks, and the red ATS block above them. These three elements form the absolute bedrock of the ground system, and they're constantly communicating with the train across that yellow, high-speed signaling network barrier.
To put a more formal definition on it, the trackside subsystem is the ground-based component of the overall ERTMS/ETCS infrastructure. It contains these core functional blocks that collaborate to manage train movement and separation. Now, while modern rail control relies heavily on onboard computers calculating those dynamic braking curves, literally none of that works without this ground-based infrastructure. It's the ultimate anchor of railway safety, providing the reliable, real-time data the train needs to safely move forward.
Moving right along to Section 2, the ETCS subsystem, or as we like to call it, our safety bumper.
The ETCS subsystem, which you'll often hear referred to as SDT on high-speed lines, standing for Sistema Distanciamento Treni, is fundamentally responsible for two things: safe space separation between trains and constant speed monitoring. Its absolutely critical, non-negotiable role is to keep high-speed trains physically separated from one another. It essentially guarantees that no two trains can ever occupy the same stretch of track under any conditions that could lead to a collision.
So, how does it actually pull this off? The core duties of the ETCS subsystem revolve entirely around automated enforcement. It doesn't just sit there and watch, it acts. The subsystem constantly monitors the train's travel against what's known as a most restrictive speed profile. If a train is going too fast or, say, approaching a danger point, the system will first issue visual and audible pre-indications and warnings to the driver. But if a driver fails to respond to those warnings within a predefined window of time, the subsystem intervenes automatically. It'll execute a service brake intervention, or in really critical scenarios, an outright emergency brake intervention, forcing the train into a safe state.
And here we can see that exact information exchange in action. The trackside infrastructure uses the GSM-R radio network antenna on the left to beam continuous data straight to the train. You'll also spot the physical track magnets, the Eurobalise, down on the ground below the train, which provide absolutely vital location reference points. Working together, these trackside elements transmit crucial permission to proceed messages, what we call movement authorities, directly into the train's cockpit, updating the driver's display in real time.
Section 3. Interlocking, or IXL, the traffic cop.
Think about it. If a train only ever traveled on a single straight track forever, our jobs would be pretty simple, right? But to get from point A to point B through complex stations, a train has options, like taking the green path 1 or the red path 2. The interlocking system's main job is to manage the line and accurately route those trains. It physically and logically configures the switches out on the track to create a highly dedicated, safe route for the train to follow.
The interlocking system achieves this through a very strict chronological process called route locking. First up, it identifies the exact origin and destination path. Second, it determines all the necessary block sections and track switches required to make that path happen. Third, it locks those sections completely, both physically and logically. And finally, only once every single thing is locked and secure, it grants the train access to the route. By treating the route as a strictly shared resource, interlocking eliminates conflicts before they can ever even occur.
I really want to hammer this concept home because it's absolutely crucial. A route is a mutually exclusive shared resource. Until a locked route is actively cleared by the occupying train moving completely out of those track sections, the interlocking system will flat out refuse to grant any other vehicle access to that path. It is a rigid, fail-safe logic designed to prevent routing disasters.
Alright, Section 4, Traffic Management, the Overseer.
Picture a bustling railway control room.
The screens you'd see form the human-machine interface for the train dispatchers. While the ETCS and interlocking systems are out there autonomously calculating braking curves and locking physical switches, human operators are sitting right here, visually supervising the entire high-speed network in real time.
The ATS, which is also sometimes called the TMS, handles the macro-level intelligence. It supervises real-time traffic circulation, it empowers dispatchers to plan, regulate, and actively optimize train movements to prevent bottlenecks and ensure everything runs right on schedule. Beyond that, it manages the overall infrastructure state and performs system-wide diagnostics. So if an interlocking equipment module or a radio block center suddenly goes down, the ATS is exactly where that diagnostic alert pops up, allowing the human operators to react swiftly.
Section 5. Subsystem synchronization, working together.
Let's bring it all together now. You have your ETCS Subsystem-R safety bumper, ensuring space separation and speed monitoring so trains simply don't collide. You have Interlocking, the traffic cop, managing and locking mutually exclusive train routes through complex switches. And finally, you have Traffic Management, the overseer, providing top-level traffic supervision, optimization, and diagnostics for the humans in the loop. Together, they create a beautifully comprehensive, layered safety and operational net right there on the ground.
But understanding the normal operation always leads us to a much deeper engineering question. When things are running smoothly, this three-pillar architecture is incredibly robust. But what happens when things go wrong? How do these synchronized trackside systems securely manage edge case failures? What happens when a crucial sensor fails or a radio link just drops entirely? How do these interconnected systems orchestrate a safe fallback state without grinding the entire country's rail network to a screeching halt? It's a fascinating puzzle of redundancy and degraded mode engineering.
Thanks, we can see an FCD.